2019. Babylon's Peer Review Award in the year 2018. Excellence in Research Award in the year 2015. Excellence in Teaching Award in the year 2013. Okay. Professor Badawi has written 5 different books on various topics on algebra. Professor Badawi has written, published about 50 papers in the reputed journals. Professor Badawi has guided about 8 students, and Professor Badawi has written book chapters as well. And Professor Badawi has given number of invited talks and keynote addresses. And yeah, he has been reviewing a number of papers in different journals, reputed journals. And also Professor Badawi has done sponsored research projects. He has a very long teaching experience, and also he has been involved in administrative works. With these few words, I welcome you, sir, for this Tamil Chelvam endowment lecture. Now the session is over to you, sir.
Okay, well, thank you very much for this nice introduction. And, you know, I mean, I am a regular customer to India, but because of the current situation, I cannot be there face to face. I hope in the near future, I will be able to meet all of you. Okay. This is, I'm not sure, do you see the screen okay? Is my slice and everything okay?
It's okay.
Okay.
Fine.
All right. So this is a talk about graph, and the title of the talk, dot product graph. Okay, so let me get to it. There is something missing here. I'm not sure, am I using the same? Yeah, I think it's the same, I hope. Okay, here's the definition. In fact, this talk relies on 2 papers, one of them in 2015, written by me, and the other paper that published in 2020 with my student. He did a master thesis on unit dot graph. Okay, so what's the definition of total dot product graph? You take your ring A will be commutative with non-zero identity, and you take R to be like n copies of A. And R will be A cross A cross A cross A n times. And if we take 2 elements, X and Y.
I'm sorry for the interruption. Control L in order to have the full screen. Control L.
Control L.
Yeah, in that full screen view. Yeah.
Fit to window. I have a view.
Oh.
Control L. Let me see. Control L. I think that's what I'm doing, is not?
Okay, okay, fine. Please continue.
Okay, just a minute. Maybe I can zoom in, zoom out.
Full screen.
How is that?
In you.
Control Shift plus F.
Yep.
Control Shift F. Okay. That's
Fine.
what full screen. Yeah, fine.
Okay.
Okay. Fine. You continue.
Yeah. Because from here it looks fine. I'm not sure how does it look from there. Okay. So R will be a product of A n times. And if you take two elements in R, X and Y, then the dot product X dot Y will be X1, Y1 plus X, you know, like the normal dot product, like the things we study in, you know, in high school or in college. You know, like X1, Y1 plus X2, Y2, keep going. And we want this element to be in A. That's the dot product. So we know what's the dot product mean. So what do we mean with the total dot product? Total dot product, we take the vertices to be R star. That means R take away the zero element. And remember that R is the product of A n times. A times A times A times A times A n times. That is what is R. And we take the zero element. And as usual, how we define we connect two vertices. We connect two vertices if the dot product is zero. So if we stop for a minute, let's assume that R, I mean, N here is 1. If N is 1, then your R will be just A. So this definition written in 1, this definition will be exactly what is the classical zero divisor graph of a ring, right? So that's exactly will be the definition of the classical zero divisor graph. All right. To follow my talk, you only need to know the definition of the total dot product. And you need to know what is R. R is a product of N copies of commutative rings. Okay. All right, then what is the zero divisor of R? Zero divisor, denote the zero divisor graph of R, or the zero dot product. If we take ZR to be the set of all zero divisor of the ring R, okay? So that's the set of all zero divisors of the ring R. And then you take ZR star to be the set of all zero divisor of the ring R, take away 0. So it follows that the classical zero divisor graph, all of you familiar with, the classical zero divisor of the ring is definitely a subgraph of the zero dot product graph. ZDR mean the zero divisor zero dot product graph. I mean, these are a crucial thing. I know I spent too much time on the first page, because if you want to follow this talk, you need to know the notation. So again, R copies of A, the total dot product R take away 0, and the zero dot product will be like you take the zero divisor of the ring R. And of course, you can construct a subgraph inside the total dot product by taking only the non-zero zero divisors of the ring R. Okay, that's what I mentioned. So here is the first result. And one thing about this kind of graph, I mean, like there is always a question, why do we study graph of rings? One of them, I mean, the graph by itself is a beautiful subject, but there is another reason. It will give you some properties of the ring. I mean, like back and forth. If I know the graph, maybe I can get some information about the ring. And if I have enough information about the ring, then maybe I will be able to construct the graph. So if you have an integral domain and R is A cross A, then the total dot product TDR mean the total dot product of the graph disconnected. So it will be disconnected, completely disconnected. Well, maybe I should not say completely, maybe it will be. Well, it's disconnected. And the zero dot product graph will equal to the classical zero divisor graph is connected. And here I mention in particular here that this A will be ring isomorphic to Z2 A. If A, then if A is Z2, then the zero dot product graph is complete. If A is not ring isomorphic to Z2, then the diameter will be 2. And the girth will be 4. Okay. The second result about that, of course, here I skipped something because all of you should be familiar what we mean with girth and diameter. Girth is the length of the shortest cycle in the graph. Like, you know, like, and what we mean with length. Length meaning the minimum number of edges you use to form a cycle. The minimum number of edges we use in order to form a cycle, that will be the length of the cycle. Okay, and the diameter, first you need to know what we mean with distance. And all of you, I think, familiar with distance. Distance mean between two vertices is the minimum number of edges we need to go from A to B. That's the distance between two vertices. And the diameter, you take like the maximum of all distances. Okay. Here is a nice, it's not maybe very difficult to prove, but this is a connection between a graph and the structure of the ring. If this A is commutative ring with 1, and R is n copies of A, then the zero dot product is equal to the classical zero divisor graph if and only if either n equal 2, this n will be 2, and A is an integral domain, or R has to be ring isomorphic to 3 copies of Z2. Z2 cross Z2 cross Z2. Okay, so this is, I call this result like a structure or a connection between the zero dot product and the structure of the ring. Okay. If you have, let A be a commutative ring with one not equal 0, that is not an integral domain, and you take R, the product of these two rings, then the following statement are equivalent. Okay, so my A is not integral domain, and R is a product of 2. Then these three statements are equivalent. If you tell me the total dot product is connected and diameter equal 3, then I know that the zero dot product is connected. I know the zero dot product is not equal to the classical zero divisor graph. I know that the girth of the zero dot product equal to the girth of the total dot product, which is 3. Okay, so these are properties when R is a product of two commutative. Okay, if A is a commutative ring and N is bigger than 3, less than infinity, and you take R to be N copies of A, then the total dot product is connected and the diameter of the total dot product equal 2. Okay, the diameter of the total dot product will be 2. And again, what's the diameter? Is the maximum of all the distances. And here also another properties for the dot product graph. Here N, because look, I study already the case when N equal 2 in the previous. So here, what about if N between 3 less than infinity? The conclusion that the girth of the zero dot product is the same as the girth of the total dot product, which is 3. Okay. And again, what's the girth? The girth is the minimum number of edges you use in order to form a cycle. And a cycle is, just as all of us know, a cycle, like you start from a vertex, you go around and you come back to the same initial vertex. Okay. Okay, here is another connection between the structure, I call it, and a graph. If you take R to be a product of N of A, and N is between bigger or equal to 2. So these statements are equivalent. If you tell me the girth of the zero divisor is 3, it's the same as if you tell me the girth of the total. The first statement, the girth of the zero dot product, 3. This will be the same as the girth of the total dot product, 3. A is not integral domain, and N has to be 2 or 3, or N bigger or equal to 3. So these two, here, how you read it, A is not an integral domain and N equal 2. This is one statement. The second statement, or N bigger or equal to 3. So the N equal 2 has to do with A is not integral domain. Okay. Here also the same problem, like what about if the girth of the zero divisor graph is infinity? Then I know that this ring A, remember that R is n copies of A. Then this A will be ring isomorphic to Z2, and this N has to be 2. The diameter of the zero divisor graph equal 1. Okay, the diameter will be 1. So if you tell me the girth of the zero divisor zero dot product of R equal infinity, then I know that A has to be Z2. I know N has to be 2. And I know that the diameter. So this is a complete characterization when the girth may be equal infinity. The same setting, what about if the girth of the zero divisor is 4? The zero dot, I keep saying zero divisor, zero dot product. Because remember the zero dot product of R, the vertices are the set of all non-zero zero divisors of R. Okay. All right. So if you tell me the girth is 4, then I know that the total dot product is disconnected. And I know that N has to be 2 and A has to be integral domain. So if I know the girth of the zero dot product is 4, I know, and look at this, I know that the zero dot product is the same as the classical zero divisor graph. And I know that the total dot product is disconnected. And I know that this N has to be 2 and A integral domain. Okay. Another property is like, what about if the same setting? What about if the zero dot product graph, the diameter is 3? So what I know about the ring A? I know that either A is not an integral domain and N equal 2, or A is integral domain and N equal 3. Okay. Okay. The same thing here, if we go to the, so we studied diameter 3, diameter 2, now diameter 3. When is the diameter of the zero dot product is 2? A has to be, is either A is integral domain that is not isomorphic to Z2 and N equal 2. A is not integral domain and N is bigger or equal 4. So these are other condition for the dot product. I keep going here so I can go and do something more. I think I have, maybe I run out. Is my time is up, or I can go for another 10 minutes, maybe?
Yeah. Up to 3 you can continue.
Up to how many minutes?
15 minutes more.
Okay, thank you. All right. Here is another connection. between structure of the ring and A. A is your ring, R is the copies of A n times. If you tell me the total dot product graph is connected and n bigger or equal to 3, then I can tell you that the diameter is 2 of the total dot product. If you tell me the diameter is 2, I tell you n has to be 3, bigger or equal to 3. Okay. Okay, this is the second part of my talk, is with my student, Muhammad Abdullah. In fact, he finished his master in algebra, but now he is in Germany working on his PhD in functional analysis. His PhD will be. Remember, we studied the total dot product, the zero dot product. What about the unit dot product? Because if you, at the same setting, if you take R to be that many, I mean, n copies of A product, and you look at the units of R, then we can define the unit dot product. So my vertices now are units. Units where in the ring R. And what is the ring R? A product of A n times. So if you take an X to be a unit in R, that means X1 has to be a unit in A, X2 has to be a unit in A, and so on. And we define the unit dot product, UDR, stand for the unit dot product. When you do the dot product, you come up with 0. Okay? So the unit dot product will be a subgraph of the total dot product. So what are the properties of this unit dot product? My student, he studied that for finite field. Like if you start with M to be 2 to the n minus 1, and your first ring will be a finite field with 2 to the n element. Okay? So the zero dot product will be the same as the classical zero divisor, and that will be KMM for a product of 2 finite field of characteristic 2. The unit dot product is the union of 1 KM. KM, I think all of you are familiar with that. KM mean a complete graph on M vertices. And that many disjoint complete bipartite graph, KMM. Okay, is the union of 1 with that. The total dot product, so if this is the case, again, I go back, a product of 2 finite field of characteristic 2, I know the structure of the zero dot product, and I know the structure of the unit dot product, and I know the structure of the total dot product. And here are some examples. Like, yes, go ahead.
That M is nothing but 2 to the power n minus 1.
Yes, this is because you know when the ring has characteristic 2, it behaves a little bit different.
Okay.
This is a
Fine,
special
fine.
case. This is a special case. In fact, we have result when the characteristic is not 2, but the characteristic 2 is like a special case. You hear me?
I am hearing you. Please continue. Please continue.
Okay. So here is an example. Like here we constructed a finite field with 4 elements. Like Z2, the polynomial over Z2 mod this ideal, then definitely this is a finite field with 4 elements. And here they are the element. I call them V. V is the generator for the element. So you have V, V square, V cube. Okay, and remember V is this element in this ring. And here is the shape of the unit dot product will be this. So we have 2 components. One of them is complete, as promised by the theorem, if you still remember it. One component will be complete, and the other one is complete bipartite. The one on the left is the complete one. The one on the right is the complete bipartite. Here is the case, Professor Shelvam, in general. If I take the prime to be not 2, because always in dealing, in fact, in rings in general, characteristic 2, it seems always has a special case. I mean, you have to treat it differently in many cases. So here, a general case, the only, the only restriction that my prime is not 2. So P can be any. So here is a product of 2 finite field. Here we're looking at. And here I have restriction on how you did not see 2 or 3 or 4 when the prime was 2. Here we have to be careful whether 4 is a factor of M or 4 is not a factor. And remember, what is M? M is P to the N minus 1. M is P to the N minus 1. Okay? All right. And here is the structure. This result tell me the structure of the unit dot product. Like in one of the cases, if 4 is not a factor of M, here is M, then I know the unit dot product will be the union of M over 2 disjoint, you know, complete bipartite, and so on. Here is another example where of characteristic different from 2, like I take only A to be Z5, and I take R to be A cross A. This is the graph of the unit dot product. As you see, it is consists of 2 complete, and 1 component will be complete bipartite. Okay, and we did that in, you know, for many cases. Like here, I did it for Z8. These are examples. And maybe it's about time for me to stop. I only thought I give you, by the way, to my best knowledge, the unit dot product graph was not generalized in general. Like here we studied the unit dot product. We only did it for Zn, or if your ring is a product of finite field. Okay, that's all we did, but we did not do it like in the total dot product. The total dot product, my ring A was like, you know, any commutative ring. So maybe some students like to investigate or do more on this unit dot product graph. And I stop here, and I thank you, and thank you for listening. And thank you, Professor Shelvam, for inviting me.
Ayman, would you like to introduce our book?
Oh, sure.
Can I share the first page?
Yes, go ahead.
You please stop, then I will share. Or you
Okay.
please let us finish the questions first.
Okay.
Sedram,
Are there any questions from participants, audience side?
Ayman, one thing, the vertex set of the unit dot product is nothing but direct product of n copies of units of A.
Yes.
Okay.
Hi, Ayman. Asir.
Hello. Hi,
Asir.
Asir.
Yeah, I have
you
a question.
You have a beard too.
Yeah.
Okay, so actually I have a question.
Go ahead.
When you
Yeah.
have consider the Artinian ring, we have a decomposition, right? Decomposition of local rings.
Okay.
So in that case, these two graphs are same, one another same, right? If you consider an Artinian ring,
Okay.
Artinian commutative ring, then it can be written as decomposition of local ring.
Yes.
Yeah,
We know
in that way, these two, especially the study of this graph, how much it is useful to study some more properties of the zero divisor graph or total graph.
Well, you know, if I thought of that, I would answer it. But I see what you mean. You mean like to generalize in even further the unit dot product.
Yes, exactly.
Right?
Yeah.
Yes, yeah, that's what I mentioned at the beginning. Maybe some of the structure we did here will be useful for the general case, because, you know, like in some of the cases, maybe your ring will be a product of field or something. You know what I mean?
Yes, yes.
So maybe this, yeah, but this will be maybe nice to investigate that for you know, further. I agree with you. Good question.
Ayman, one thing. Have you ever considered A1 times A2 instead of A times A?
You mean different rings?
Yeah, different components, because
well,
Asir question ultimately leads to the generalization of different components.
yeah, I know, but here we have a problem with the definition, because when you add, remember the dot product, you're gonna add.
Yes.
Unless you take A2 to be
same addition.
Yes, as a subring. It has to
Yes.
be a subring, like A2 subring of A1, A3 subring of A2. Then it will work out.
Yeah, fine.
Then we are working in one, because the problem with the dot product.
And of course, this is the graph wherein the multiplication and addition is combinedly used.
Yeah, definitely.
Yeah, that's the case.
Yeah, because when I do the dot product, I'm adding, and the addition has to be defined in one, you know. Yeah, that's where, in fact, I thought about that, but then I could not do it because I have to redefine dot product.
You can stop. I will share the first page of the wrapper page.
Okay.
Thank you, Professor. Thank you for a wonderful talk. It was very nicely presented. Very interesting. Thank you for the wonderful talk. Thank you very much.
Thank you very much. Okay, let me stop. So I stop.
Ayman, can you see my screen?
Yes,
Yeah,
I see. Did I stop sharing?
I think. Are you able to see my screen?
I am able.
Yeah, please.
Yeah, this is, by the way, a book that Professor Shelvam and Asir and our colleague David Anderson and myself wrote, and this is a graph from rings. And this book is, to our best knowledge, will be the first book in literature about graphs from rings. And we are so happy that this book, I mean, this book took maybe 6 years to accomplish. We started in 2014, and so we are proud of this work, and I want to thank my colleague, Professor Shelvam and Asir, for, you know, for such wonderful job in you know, producing the book.
Actually, Ayman Badawi is the corresponding author. He has taken the much pain of doing all these things. So he is the corresponding author of the book. Really, we too wanted to thank Ayman at this moment.
Well,
Okay.
we thank all of you.
All of you, yeah.
all of us
Okay.
definitely contributed to this book.
Okay, fine. And
Yeah.
it is
And I think the book will be available in November in
27.
a print.
27.
Yes, November 27, exactly. Yeah.
Fine. Okay, thank you for your nice talk. Still,
you.
I feel that there are very much opening in the definition of the total dot product and unit dot product, as well as zero dot product.
Yes, I think there will be, like, I hope some student or, you know,
Yeah.
sorry, to look up into that, and maybe it's worth it.
Okay.
To study as you suggested, with one restriction, that A2 need not to be A1, but inside A1, and so on. So maybe this will, you know, I don't know what kind of structure we will get. Okay.
Hello, Professor Badawi. Vinayak Joshi
Hello.
here. Congratulations.
Hi, thank you.
Vinayak Joshi from Pune University.
Yeah.
Thank you. Yeah, I know him. I think we met a few times.
Nice work. Yeah.
Hi, Badawi, Professor Balakrishnan from Bharatidasan. Badawi, you met
Yes.
Professor Balakrishnan from Bharatidasan University.
Definitely.
Yeah, in our
Nice
workshop. Yeah, we met.
Yeah, I mean, of course.
Ayman, nice meeting you.
Thank you. Nice to see you again.
Congratulations on your book.
Thank you very much.
And
Thank
I'm
you.
very happy to learn through Tamil Chelvan that you had been the ringleader.
Well, thank you. Thank you very much.
Ranjani, you please.
Thank you, sir. Thank you for giving us such a wonderful lecture. I also extend my gratitude to Professor Dr. Seduraman, who initiated the session. Thank you, sir.
Thank you.
So, shall I conclude now?
Yeah,
okay, sir.
Session by 3:15.
Yes,
we will join by 3.
Okay, sir. The next session starts by 3:15. The chairperson for the next session is Professor Dr. Madhumangal Pal, and the resource person is Dr. R. Venkatesh. Thank you, one and all.
Thank you.
I'm sorry, I have duties to attend, you know, because we start the college, the university and we do face to face. So, you know, I apologize for my colleague for not being able to attend for some of the talks. My apology, but it's my control because I teach too.
Okay.
Okay, thank you. Bye-bye.
Thank you, Ayman.
Thank you,
Ayman,
thank
thank you. Very soon, let us have the opportunity of meeting together in person.
I hope
I
so.
pray. I hope so.
I hope so. Thanks a lot.
Fine.
Bye-bye.
Thanks. Thank you. Thank you. Bye-bye.
Leave பண்ணிக்கலாமா sir?
Ayman, bye.
Please, Sundaranar, thank you.
Thank you, sir.
very much.
Congratulations for the book.
Fine.
Wonderful.
Thank you.